it's the probability that your arrival occurs between 0 and 0 plus dt. So to see that this is true, you can just use Bayes' rule and notice that lambda dt is exactly the probability that t, your first arrival, occurs between 0 and 0 plus dt. So conclusion, so long as a light bulb is still functioning, it's as good as new. You can think of if it hasn't occurred till now, if the light bulb hasn't died till now, then you could just start the clock over on it, and in that case it would be as good as new, and wait for it to burn out. So if only warranties worked that way. Furthermore, from the equation above, you can see that lambda is the probability that t is in dt given that t is greater than t divided by dt. And so this is the instantaneous rate of success, right? It's a ratio of the probability of having an arrival in dt, given that t is greater than t, divided by the length of time. So that's sort of a calculus way of thinking of instantaneous rate. Notice that it's not dependent, lambda is not dependent on t here, and so lambda is the same for any t, and so lambda is just a constant rate for your process. So we also looked at a relationship of x being geometric p. So px converges to exponential 1 as p goes to 0. Now, today we'll continue to talk about that. And furthermore, we'll talk about the expectation invariance of exponential lambda and the gamma distribution. So we, of course, have the Taylor series for e to the x, and that gives us a relationship 1 minus p is approximately e to the minus p for small p. So now the probability that px is greater than pk is approximately e to the minus pk. And if you just think of t as being equal to pk, this says that the probability that px is greater than t is approximately e to the minus t. So so now so e to the minus t has this graph shown here, and so we know that the density of f of t is 1 times e to the minus 1t, and so so we conclude here that px is converging to the exponential 1 as p goes to 0. So now the expectation invariance of the exponential is just a calculation, it's just an integral, and I've provided the calculus details at the end of the note because it's really not that interesting. It's just basically integration by parts. So the main thing is the result. The expectation of t is 1 over lambda. The variance of t is 1 over lambda squared. And you can actually see that this holds if you concentrate on the case where lambda is 1. And there, in that case, you know that exponential 1 is approximately the change of scale px. And so we know that for x geometric, expectation of x is 1 over p, and so the expectation of px is pex, which is just 1, so that obviously converges to 1 as p goes to 0. So so this makes sense that the center of your distribution px would converge to the center of the limit exponential 1, and that is the case here because you expected the expectation of of exponential 1 to be 1 over lambda, or 1 over 1. Similarly for variance of px, the p pulls out as a square, just giving you then p squared times q over p squared. P's cancel, q goes to 1 as p goes to 0. So indeed here the variance of t looks like it should be 1, and it is. So we can think of lambda, so by this definition, lambda is 1 over the expectation of t. It makes sense if the instantaneous rate is a constant everywhere, then it should just be 1 over the average arrival time. So we did an example. T is the waiting time in minutes until a blue Honda arrives at a toll gate starting at noon. The waiting time is an average 2 minutes. Find the probability that T is greater than 3. So you look there, the expectation of T is 2 minutes, so lambda is 1/2. So T is exponential 1/2. So then the probability that T is greater than 3, that's the survival function, is e to the minus 1/2 times 3. So that is e to the minus 3/2. So now onto the gamma function. So the gamma function is a sum of IID exponentials. You can think of it as the time of the Rth arrival of a Poisson process, Poisson lambda t, that is. So the lambda from gamma is the same lambda as in the Poisson here. So TR could be the time when the Rth light bulb dies in a picture. So the x's in this picture are the arrivals occurring at time 1, time 2, times 3, and the inter-arrival times are D1, are W1, W2, W3. Those are all independent exponentials. Oh my goodness. Sorry about this. What did I do? Okay. So we have T1 is W1, T2 is W1 plus W2, T3 is the sum of the 3 W's. So let's review Poisson process, or Poisson random scatters. So n sub t is Poisson lambda t, and that is the number of arrivals in time t, where the rate of arrivals is lambda. And the probability that nt is n is just given by the Poisson formula. So now let T1 be the waiting time until a blue Honda enters a toll gate starting at noon. The waiting time is an average 2 minutes. Find the probability 3 blue Hondas arrive in 8 minutes. So we know lambda is 1/2. We know we have a Poisson 4. So the probability that N8 is 3 is just given by the Poisson formula, e to the minus 4, 4 to the 3rd, 3 factorial. So now that we're good with Poisson, let's go back to gamma distribution. So this is the key of the lecture here. If TR is gamma R lambda, NT is Poisson lambda t, and W is exponential lambda, the probability that TR is in dt, in other words, the probability that the Rth arrival occurs in dt, means that I have R minus 1 arrivals before t, and I have 1 arrival in dt. In other words, I have and these are independent. So this is the probability that nt is R minus 1, that I have R minus 1 arrivals in time t, and given that my final arrival is greater than t, W is in dt, which by the memberless property, that is just lambda dt. So we get the formula given here, and necessarily then the density is this before the dt. So So now this formula is fine, this density is fine, except that generally the gamma is not only for r is a positive integer, but actually for r a positive real number. So we're going to have to introduce the gamma function to generalize this definition of gamma that we've been talking about. So we're going to define the gamma function, gamma r, to be r minus 1 factorial when r is a positive integer. And so in particular, when lambda is 1, the density has a constant and variable part. The variable part's a function of t. And of course, the integral of the density is 1. So if I pull out my constant and I cross multiply, you get that gamma of r is this integral here. And this is actually the definition of the gamma function. So this allows us to define the gamma function for r greater than 0 as, instead of the 1 over r minus 1 factorial, it will be 1 over gamma r, lambda to the r, t to the r minus 1, e to the minus lambda t. That is the density. And of course, t is greater than 0 here, which I should write. Okay, so if tr is gamma r for lambda equals 2, just making sure you understand find the density. So we just plug everything in. Note that gamma 4 is 3 times 2. 2 to the 4th power is 16, so that gives us 8 over 3, t cubed e to the minus 2t. And so we finally get the density now, final form. And if you wanted to find the probability that tr is greater than t, you might think that you could just integrate from t to infinity of the density, and of course you can do that, but there's a much better way to do it, and that's the following key observation, that the probability that the rth arrival occurs in longer than t minutes is equivalent to the Poisson, the number of arrivals in t minutes is less than r. And so here I've tried to show that in this picture here. So I necessarily have less than or equal to r minus 1 arrivals before t. So that's equivalent to saying that nt is less than r. And the thing is that to find the probability that nt is less than r is very easy, because it's just a discrete distribution. So, for example, probability that t4 is greater than 7 in this case is equal to the probability that n7 is less than or equal to 3, which you can find easily. And then we finished with this problem here. Suppose customers are arriving at a ticket booth at a rate of 5 per minute. According to a Poisson arrival process, find the probability that starting from time 0, the 9th customer doesn't arrive within 5 minutes. So the probability that T9 is greater than 5 is equal to probability that N5 is less than 9. And we can just write out what using the Poisson formula. And secondly, at least one customer arrives within 40 seconds after the arrival of the 13th customer. So it's after the arrival of the 13th customer, we reset the clock. So using the memoryless property, we reset the clock, and now it's just the probability that the 14th exponential, 14th waiting time, the 14th waiting time, which is exponential lambda, is less than 2/3. So 2/3 is 40 seconds, 2/3 minutes. And so that's just 1 minus the probability that the 14th waiting time is greater than 2/3, which is just a survival function here. And easy peasy, right? Have a great weekend, and I'll see you on Monday.